Hello everyone, my name is Jonathan Flores and this video presents the implementation of an 8-bit binary counter using VGL in Quartos Prime and Cuesta Intel FPGA. The goal is practice to design, simulate, and test synchronous counter that increases its value on each clock cycle and resets to 0 when the reset signal is active. We start by creating the main VGL file named bind count VHG. Inside the entity we define the inputs, outputs, and the clock 50 MHz input as the main clock, the reset clock input as a synchronous reset, the counter output which represents the 8-bit count results, and the clock out. And the architecture section with two processes. The first one is clock divider, which reduces the input clock frequency to make the output observable in real time on the FPGA. The second process is the binary counter, which increments the value of counter at each rising edge of the new clock signal. And once we compile the VG nets, we generate the TextBind file automatically with Quartos tools and edit it to simulate clock and reset signals. In this file, the clock toggles every 10 nanoseconds, creating a 50 MHz frequency, and the reset is applied briefly at the beginning of the simulation to ensure correct initialization. Then the project is then compiled successfully in Quartos, and as we can see in the compilation summary, all synthesis stages complete with 0 errors, confirming that the design is syntactically and logically correct. Once the design is compiled, we open Cuesta Intel FPGA for simulation. We select work in this library and select the two archives we have here. Then we recompile and then start simulation. Again, we select work and the VHD test, resolution default, and apply full visibility to all models. Now we're going to transfer our outputs and inputs to the wave view, and we're going to change to binary, the counter. Now we run all for 3 seconds and then we stop the simulation. And the waveform window shows the clock reset and the counter signals. At first the counter remains at 0 while reset is active. After a reset is released, the counter increments sequentially from the 8 zeros to the 8 ones, and then restarts at 0, demonstrating proper rollover behavior. And as we can see, this is the reset. The restarts at 0. This confirms that the circuit behaves as expected according to the design specification. After verifying the simulation, the design is programmed into a FPGA board, and each LED on the board represents 1 bit of the counter output. When the system runs, the LEDs light up in a binary sequence that visually represents the counter increment. When the reset button is pressed, all LEDs turn off, resetting the counter to 0, releasing the button resumes normal operation, and the LEDs continue to toggle according to the clock signal. This hardware behavior perfectly matches simulated results, validating the correct synchronization between software and physical implementation. And that's it. Thank you so much.